In this video, we will use the concept of the rate-determining step to discuss the factors that can affect the rate of an E2 mechanism. And then in the next video in this series, we will see how to apply this material to problems that are typical of what you might see on exams. Now, in these two videos, for purposes of comparison, we will also be discussing factors that affect the rates of SN2 and SN1 reactions. That's material that I already introduced in my previous series on SN2 and SN1 reactions. Now, in those previous videos, we saw that a key concept here is the rate-determining step. How would you define the concept of rate-determining step? Here's the answer. The rate-determining step is the slowest step in a reaction. You could also call it the most difficult, hardest step in the reaction. This is important because anything that affects the rate-determining step will affect the rate of the reaction, and also anything that does not affect the rate-determining step will not affect the rate of the reaction. Now, the factors that favor E2 reactions are in many ways similar to the factors that favor SN2 reactions. So I think I'll start here by briefly reviewing the factors that favor SN2 reactions. So to start with, what would you say is the rate-determining step for an SN2 reaction? What's the rate-determining step for an SN2 mechanism? Here's the answer. That is kind of a trick question because you should know there is only one step in an SN2 mechanism. Since there is only one step in an SN2 mechanism, that one step is the rate-determining step for SN2. So here's an example of an SN2 mechanism. There's only one step, and this single step is the rate-determining step for SN2. So remember, anything that affects that rate-determining step will affect the rate for an SN2 reaction. Do you remember how is an SN2 reaction affected by leaving group quality and nucleophile quality? Here's the answer. Here's the answer. And now, pause the video and see if you can justify each of these statements. How would you justify these statements? Well, here's how. Notice that the leaving group participates in the rate-determining step for SN2. Therefore, leaving group quality matters for SN2 because anything that affects the rate-determining step will affect the rate of a reaction. And as a result, an SN2 reaction requires a good leaving group. How would you justify this statement? Here's the answer. You would justify it by saying that the nucleophile participates in the rate-determining step for SN2, and therefore nucleophile quality affects the rate of an SN2 reaction, and therefore an SN2 reaction requires a good nucleophile. Now let's try a similar analysis for E2. So first question, what is the rate-determining step for an E2 mechanism? Pause the video and articulate what is the rate-determining step for an E2 mechanism. Here's the answer. Well, here's an example of an E2 mechanism that we dealt with in an earlier video, and the key thing to remember is that there's only one step in an E2 mechanism. There's only one step in an E2 mechanism, so that single step must be the rate-determining step. There is only one step in an E2 mechanism, so that single step is the rate-determining step. That analysis is quite similar to the analysis for SN2, because SN2 is also a one-step reaction. Remember, anything that affects that rate-determining step will affect the rate of the reaction. So, question, does leaving group quality matter for an E2 reaction? What do you think? Here's the answer. Yes, leaving group quality matters for an E2 reaction. How would you justify this? The leaving group participates in the rate-determining step for E2. Therefore, leaving group quality matters for an E2 reaction. Does an E2 reaction require a good leaving group? Here's the answer. Yes, an E2 reaction requires a good leaving group. Justification: because the leaving group participates in the rate-determining step. Question: first of all, notice that for E2, we're not going to talk about nucleophile quality, will we? There is no nucleophile in an E2, so what should we talk about here? We should talk about base quality. So my question is, do you think that base quality matters for an E2 reaction? Here's the answer. Yes, the quality of the base matters for the rate of an E2 reaction. How would you justify that statement? Because the base participates in the rate-determining step for E2. Since the base participates in the single rate-determining step for E2, the quality of the base affects the rate of the E2 reaction. So do you think that a E2 reaction requires a strong base? Do you think E2 requires a strong base? Yes, E2 requires a strong base. Justification: because the base participates in the rate-determining step for E2. So notice that whereas SN2 depends on nucleophile quality, E2 depends on base quality, because a SN2 reaction uses a nucleophile, whereas an E2 reaction uses a base. Do you remember the difference between those? Remember, this is called a nucleophile because it's joining the other molecule, whereas this is called a base because rather than joining the other molecule, it's taking a proton from the molecule. The base is similar to the nucleophile in that they both donate electrons. For completeness, now would be a good time to go through the same analysis for an SN1 mechanism. So now would be a good time to pause the video and try to go through this entire analysis for SN1, the same analysis that we went through for E2 and SN2. Determine the rate-determining step and determine the effect of leaving group quality and nucleophile quality on an SN1. I hope you paused the video and tried to work on that. Here's some answers. What is the rate-determining step for SN1? Well, remember that an SN1 mechanism has two steps. There's two steps in an SN1 mechanism. So we have to decide which is the slow step, which is the difficult step. And the answer is the first step is the slow step. This first step is the slow step because this is the step that creates formal charges. You should know that nature, again, as we've talked about in the past, nature prefers things to be neutral. Nature dislikes forming formal charges. Notice that this molecule here has no formal charges, but when the leaving group leaves, that creates two formal charges, a positive formal charge on the alpha carbon and a negative formal charge on the leaving group. Since this first step creates two formal charges, this is the slow, difficult step. The second step is easy because the second step gets rid of two formal charges. You can see the second step gets rid of the formal charge on the nucleophile and on the alpha carbon. So the second step is a fast, easy step. It's the first step, which is the slow, difficult step, forming the carbocation. By the way, this first step is also difficult because the carbocation has an incomplete octet, and that's also disfavored. So the rate-determining step for SN1 is the first step. That's the step where the leaving group leaves the alpha carbon. You could also say that's the step where we form the carbocation. The rate-determining step for SN1 is carbocation formation. So can you use that idea to justify these answers? I hope you tried that. Well, notice that the leaving group participates in the rate-determining step for SN1. Therefore, leaving group quality does matter for an SN1, and an SN1 reaction does require a good leaving group. But notice, here's the interesting thing, the nucleophile does not participate in the rate-determining step for SN1. The nucleophile does not participate in the rate-determining step for SN1. It participates in the fast, easy step, the second step, not the slow, difficult step. Well, remember we've discussed anything that does not affect the rate-determining step will not affect the rate of the reaction. Since the nucleophile does not participate in the rate-determining step for SN1, nucleophile quality does not matter for an SN1 reaction. And therefore, an SN1 reaction does not require a good nucleophile. An SN1 reaction can work even with a poor nucleophile because the nucleophile is not participating in the rate-determining step for SN1. Anything that does not affect the rate-determining step will not affect the rate of the reaction. So I think this is probably the most surprising idea that we have on the screen right now. The most surprising idea is that quality of the nucleophile doesn't matter for SN1 and that the SN1 doesn't require a good nucleophile. And that's because the nucleophile does not participate in the rate-determining step for SN1. Most of these other ideas here on the screen, I think, are fairly intuitive, and they match, I think, what you would expect. So to summarize, leaving group quality matters for all three reactions. Leaving group quality matters for E2, SN2, SN1. All three of these mechanisms require a good leaving group. Base quality matters for E2, and E2 requires a strong base. Nucleophile quality matters for SN2, and SN2 requires a good nucleophile. But surprisingly, nucleophile quality does not matter for SN1, and SN1 does not require a good nucleophile. Now, how can you tell whether a leaving group is a good leaving group or not a good leaving group? Well, here's what we discussed in the first video in this series. You should have memorized that neutral chlorine, neutral bromine, and neutral iodide are good leaving groups. You should have memorized that neutral sulfonates are good leaving groups. We've illustrated those ideas in the previous videos in this series. And you should also know other neutral atoms are usually not acceptable leaving groups. So usually, if you haven't specifically learned that a neutral atom is an acceptable leaving group, we usually guess that it's not an acceptable leaving group. There are other acceptable leaving groups, but you have to learn reasons why those are acceptable. Obviously, this is not a complete discussion of how to identify a good leaving group, but this is complete enough for our purposes right now. All three of these mechanisms require a good leaving group. Now, how can you tell whether you have a strong base or a weak base? How can you tell whether you have a good nucleophile or a poor nucleophile? Well, you can tell if you have this table memorized. Remember, you need to have the species at the top of each column memorized. So notice that these columns here tell you who the poor nucleophiles are and who the good nucleophiles are. For example, neutral oxygen is a poor nucleophile, and all the other species are good nucleophiles. Also, the table tells you who a strong base is and who a weak base is. So the only strong bases in this table are O- and N-. The only strong bases in the table are O- and N-. All the other bases in the table are weak bases. Now, there are other strong bases that you'll learn about later in your course, but for our purposes right now, the only strong bases we need to discuss right now are O- and N-. So you can use this table. If you have the complete table memorized, that will tell you which are poor nucleophiles and which are good nucleophiles, which are weak bases and which are strong bases. So it's important to have this table completely memorized, partly for that reason. So have you noticed that there are no E2 reactions in this column? And there are no E2 reactions in this column. Only the right-hand column contains E2 reactions. So please pause the video and explain why that is. Explain why are there no E2 reactions in this column? Why are there no E2 reactions in this column? Why is the right-hand column the only column that allows E2 mechanisms? Well, here's the answer. It's because E2 requires a strong base. E2 requires a strong base. Well, notice that this left-hand column is for a weak base. So this weak base cannot carry out an E2 mechanism. And the middle column is also for weak bases. So the species in this middle column also cannot carry out an E2 mechanism. E2 requires a strong base. Only the right-hand column contains strong bases. So only when we're in the right-hand column is it possible for us to have an E2 mechanism. Remember, E2 requires a strong base because the base participates in the rate-determining step for E2. Okay, so I promised you that by covering this material, we would get a better insight into the material, and here's a good example of that. Hopefully now we have a better insight into this table. Now you understand this table better. Now you understand why E2 only occurs in the right-hand column of the table. On the other hand, notice that having a strong base doesn't guarantee E2, does it? Even when you have a strong base, it's still possible to have an SN2 reaction. So notice that a strong base is a requirement for E2, but a strong base is not a guarantee of E2. That's why you actually have to have the table memorized. You have to have the table memorized so you can tell, even with a strong base, whether you're going to carry out an SN2 or an E2 mechanism. By the way, there are no SN2 mechanisms in this left-hand column. Why not? Here's the answer. SN2 requires a good nucleophile. Since SN2 requires a good nucleophile, we can't have an SN2 in the left-hand column because this left-hand column is for poor nucleophiles. SN2 can only occur in the middle and the right-hand column because those are the columns that involve good nucleophiles. Notice that in this left-hand column, we can carry out an SN1 mechanism, even with a poor nucleophile. Why can you have an SN1 mechanism, even with a poor nucleophile? Answer: because an SN1 mechanism doesn't require a good nucleophile, because the nucleophile doesn't participate in the rate-determining step for SN1. An SN1 reaction does not require a good nucleophile. On the other hand, notice that a good nucleophile doesn't prevent an SN1 reaction. Sometimes we can get an SN1 reaction with a good nucleophile, but we can also get an SN1 reaction without a good nucleophile. Because these patterns are so complicated, that's why we have to actually memorize the table to reliably figure out the mechanism. All right, so again, I hope that what we've just been talking about helps you to feel that you have a better insight and understanding into where this table is coming from. By the way, we can now explain what the number 2 stands for in the term E2 mechanism. Do you know what the number 2 stands for in this term? Here's the answer. Well, we know that this number does not represent the number of steps in an E2 mechanism. After all, we know that an E2 mechanism consists of only one step, not 2 steps. So we use the number 2 here because 2 species participate in the rate-determining step for E2. There are 2 species that participate in the rate-determining step for E2. The substrate that includes the alpha carbon and the base. So the 2 species here would be the OCH3- and the substrate that includes the alpha carbon. 2 species participate in the rate-determining step for E2. That's what the number 2 represents in the term E2. E2 has the number 2 in its name to represent the idea that 2 species participate in the rate-determining step for E2. Next question, what does the number 2 represent in the term SN2 mechanism? Here's the answer. It represents the same idea as for E2. Again, in an SN2 mechanism, there are 2 species that participate in the rate-determining step, the nucleophile and the substrate that includes the alpha carbon. 2 separate species participate in the rate-determining step for SN2, and that's why the mechanism has the number 2 in its name. Next question, what does the number 1 stand for in the term SN1 mechanism? Here's the answer. For an SN1 mechanism, only 1 species participates in the rate-determining step. Only the substrate, that's the molecule that includes the alpha carbon, only the substrate participates in the rate-determining step. Notice that the nucleophile doesn't participate in the rate-determining step. Only 1 species participates in the rate-determining step for SN1. That's what the number 1 represents in this term. For completeness, let's also review what does the capital E stand for in the term E2. Do you remember? Here's the answer. As we discussed in an earlier video, the capital E stands for elimination. An elimination reaction is a reaction in which 1 or more groups are eliminated and no groups are added. Well, E2 is an elimination reaction because we eliminate two groups. We eliminate the leaving group and the beta hydrogen, but we don't add any groups to replace them. What does the S stand for in SN2? Answer: it stands for substitution. What does the S stand for in SN1? It also stands for substitution. A substitution reaction is a reaction in which one group is substituted for another group. In an SN2 reaction, a nucleophile is substituted into the position formerly occupied by the leaving group. And also for an SN1 reaction, a nucleophile is substituted into the position formerly occupied by the leaving group. So these are both substitution reactions, whereas E2 is an elimination reaction. And again, for completeness, do you remember what the capital N stands for in these terms? Here's the answer. The capital N stands for nucleophilic. These are referred to as nucleophilic substitutions because the thing that's doing the substituting is a nucleophile. In this example, the thing that substitutes into the position formerly occupied by the chlorine is a nucleophile. And again, in this example, the thing that substitutes into the position formerly occupied by the chlorine is the nucleophile. So these are called nucleophilic substitutions. So now we've reviewed what all the letters and numbers stand for in the terms E2, SN2, and SN1. Moving on, in the SN2 series, I discussed the big obstacle to SN2 reactions. What would you say is the big obstacle to SN2 mechanisms? Here's the answer. I would say that the big obstacle to SN2 is steric hindrance. Steric hindrance that blocks the nucleophile from joining the alpha carbon. Remember that steric hindrance is a fancy term for things getting in each other's way. How would you justify this statement? I hope you tried to justify it using the rate determining step. Remember that the nucleophile has to join the alpha carbon during the rate determining step for SN2. Therefore, anything that blocks the nucleophile from joining the alpha carbon, like steric hindrance, would be likely to have a big effect on SN2. So that's a partial justification for why steric hindrance that blocks the nucleophile from joining the alpha carbon is a big obstacle for SN2. It's a big obstacle because the nucleophile has to join the alpha carbon during the rate determining step. So do you remember what types of alpha carbons are best for SN2 and what types of alpha carbons are worst? Primary, secondary, tertiary. How would you rank the alpha carbons for SN2? Here's the answer. Methyl alpha carbons are best for SN2 because they have the least steric hindrance. Tertiary alpha carbons are worst for SN2 because they have the most steric hindrance. In fact, SN2 is impossible for a tertiary alpha carbon. So I've crossed out tertiary here. SN2 only works for methyl primary and secondary alpha carbons. Now, let's think about E2. So here's the question. Would we expect steric hindrance to be as big a factor for E2 as for SN2? I think I'm just going to give you the answer. The answer is that steric hindrance is not a big obstacle for E2. Steric hindrance that blocks the base from taking the beta hydrogen is not a big obstacle to E2. So I encourage you to pause the video and try to explain this contrast. See if you can explain why steric hindrance would be a big obstacle for SN2 and not for E2. This is a little bit difficult. This is more difficult than the questions I've asked you earlier, so you might have difficulty with this. But take a few seconds at least to try to explain why steric hindrance is not a big obstacle to E2. Well, now we'll discuss. Now, the base does take the beta hydrogen in the rate determining step. The base does take the beta hydrogen in the rate determining step, so you might expect that steric hindrance that blocks the base would be a big factor in E2. So why isn't it? Well, remember the difference between what a nucleophile has to do and what a base has to do. Both a nucleophile and a base are electron donors. So how are they different? The nucleophile has to join the other molecule. The base only has to steal a proton from the other molecule. Well, do you see, you have to get closer to the other molecule if you want to join it than if you want to take a proton. That's the key. In order for the nucleophile to actually join this other molecule, it has to get very close to the other molecule. Obviously, the nucleophile has to get very close to the other molecule if it's actually going to join the other molecule. But this base is not going to join this molecule. It's just leaning in, so to speak, grabbing the proton, and then running away, so to speak. The base only has to get close enough to lean in and grab the proton. It doesn't have to get close enough to actually join the carbon chain. And that's why steric hindrance is not such a big deal here. It doesn't matter if there's a lot of steric hindrance, or it's less important if there's a lot of steric hindrance here. It's true that steric hindrance would make it difficult for the base to get close to this molecule. But the base doesn't have to get that close to the molecule if all it's going to do is take a proton. Okay, so we've seen that steric hindrance is a big obstacle to SN2, but it's not a big obstacle to E2. And the reason for that is that steric hindrance makes it difficult for a base or nucleophile to get close to the other molecule. But that's less important for E2 than for SN2. A nucleophile has to join the other molecule, which means it has to get very close to the other molecule, and that is greatly hindered by steric hindrance. The base doesn't have to join the other molecule, it just has to take a proton from the other molecule. The base doesn't have to get as close to the other molecule in order to do that, and so steric hindrance that blocks the base is not as big a factor in slowing down an E2 mechanism. As a result, E2 is possible for primary, secondary, or tertiary alpha carbons. E2 is possible for any of these types of alpha carbons. Even an alpha carbon with a lot of steric hindrance, like a tertiary, does not prevent an E2 reaction from occurring. So we've seen before that tertiary alpha carbons have too much steric hindrance for SN2, but they don't have too much steric hindrance for E2 because steric hindrance is not a big obstacle for E2. By the way, for a different reason, E2 is impossible for methyl alpha carbons. E2 is impossible for a methyl alpha carbon. This is completely unrelated to steric hindrance. Pause the video and figure out why E2 is impossible for a methyl alpha carbon. Well, remember what happens in an E2 mechanism. In an E2 mechanism, the base takes the hydrogen from the beta carbon. But notice that a methyl carbon, when there's a methyl alpha carbon, there is no beta carbon. A methyl carbon is defined as a carbon that's not attached to any other carbons. A methyl carbon is a carbon that's not attached to any other carbons. Here's a methyl alpha carbon. It's not attached to any other carbons, so when there's a methyl alpha carbon, there is no beta carbon. An E2 reaction requires both an alpha carbon and a beta carbon. So obviously E2 is impossible when you have a methyl alpha carbon, because then there wouldn't be a beta carbon. That has nothing to do with steric hindrance. Okay, so E2 is impossible for a methyl alpha carbon, but it is possible for primary, secondary, or tertiary alpha carbons. Now let's discuss SN1. We saw that steric hindrance was the big obstacle to SN2. Do you think steric hindrance is a big obstacle to SN1? Answer, no it isn't. Why not? Well, steric hindrance that blocks the nucleophile from joining the alpha carbon is not a big obstacle for SN1 because the nucleophile doesn't join the alpha carbon in the rate determining step. In SN1, the nucleophile joins the alpha carbon in the second step, which is not the rate determining step. So steric hindrance that blocks the nucleophile is not a big obstacle for SN1 because the nucleophile is not joining the alpha carbon in the rate determining step. So what is the big obstacle for SN1? Do you remember? I talked about this in the SN1 series. The big obstacle to SN1 is stabilizing the carbocation. Justification? Well, remember, in the rate determining step, we're forming the carbocation. That's why this was a slow step. This first step is a slow step because it's difficult to form this carbocation. Nature doesn't like forming a carbocation because it involves forming a formal charge, and also because the carbocation has an incomplete octet. So anything that helps to stabilize that carbocation will help to speed up an SN1 reaction. So how would you rank the alpha carbons for SN1? Primary, secondary, tertiary, and methyl, which are the best alpha carbons for SN1? Here's the answer. Tertiary alpha carbons are best for SN1 because tertiary carbocations are the most stable. Methyl and primary alpha carbons are worst for SN1 because methyl and primary carbocations are the least stable. In the SN1 series, we learned that substitution with carbon chains stabilizes carbocations. The most substituted carbocation is the most stable, so the most substituted alpha carbon is best for SN1. In fact, SN1 is actually impossible for a methyl or a primary alpha carbon because that would involve forming an overly unstable carbocation. Primary carbocations and methyl carbocations are too unstable usually to actually even be formed. In the SN1 series, we also discussed that if you can form a resonance-stabilized carbocation, that is very favorable for an SN1 reaction. So the big obstacle for an SN1 reaction is stabilizing the carbocation. Stabilizing the carbocation is not an issue for E2. Question: why is stabilizing the carbocation not an issue for E2? I hope that was an easy question for you. The answer is an E2 mechanism never forms any carbocation intermediate. Notice that in this E2 mechanism, we never form a carbocation intermediate. And in the SN2 mechanism, we never form a carbocation intermediate. Only the SN1 mechanism forms a carbon with a positive formal charge. The SN1 mechanism forms a carbon with a positive formal charge, a carbocation intermediate. In the E2 mechanism and the SN2 mechanism, we never form a carbon with a positive formal charge, so there is no carbocation intermediate. So obviously stabilizing the carbocation intermediate can't be an issue if you're not even forming a carbocation intermediate. Remember that a carbocation is a carbon with a positive formal charge, not just a delta positive charge. We have some delta positives here, but no positive formal charges on any carbons. So there's no carbocation intermediate in E2 or SN2. So we've seen that steric hindrance is not a big obstacle to E2. And obviously the carbocation is not an issue at all for E2. So what is the big obstacle for E2? Well, it turns out there is nothing that is convenient to consider a big obstacle for E2. When you're thinking about SN2, it's helpful to think of steric hindrance as the big obstacle to SN2. When you're thinking about SN1, it's helpful to think of stabilizing the carbocation intermediate as the big obstacle to SN1. There's no one factor that is particularly convenient to think of as the big obstacle for E2. Notice that this table in the handout summarizes some of what we've been talking about here. The big obstacle for SN2 is steric hindrance. The big obstacle for SN1 is stabilizing the carbocation. And the big obstacle for E2, there's nothing particular. There's nothing in particular that is helpful to think of as the big obstacle for E2. Now, notice that in this table, there are no SN2 reactions in the bottom row. There are no SN2 reactions in the bottom row of the table. Why not? Because we've learned that SN2 reactions are impossible for tertiary alpha carbons because tertiary alpha carbons have too much steric hindrance for SN2. The big obstacle to SN2 is steric hindrance. That helps us to understand the bottom row of this table. Now, notice that if you look at the first row of the table, there are no SN1 reactions in the first row of the table. Why are there no SN1 reactions in the first row of the table? Answer: because we've learned that SN1 reactions are impossible for methyl and primary alpha carbons, because methyl and primary carbocations are too unstable to be formed. Since we can't form a methyl or primary carbocation, we can't do an SN1 reaction with a methyl or primary alpha carbon. Remember that if the carbocation is resonance stabilized, that would be an exception to that pattern. You can carry out an SN1 reaction on a primary alpha carbon if it would form a resonance stabilized carbocation. So now we see why there's no SN1 reactions in the top row of the table. But notice that there are E2 reactions in all 3 rows of the table. Why? Why does it make sense that there are E2 reactions in all 3 rows of the table? Because we've learned that E2 is indeed possible for primary, secondary, or tertiary alpha carbons. E2 is possible for all of these types of alpha carbons, and that's reflected in the fact that E2 appears in all 3 rows of the table. Tertiary alpha carbons don't have too much steric hindrance for E2 because steric hindrance is not a big obstacle for E2. And we don't need to worry about carbocation stability for E2 because an E2 doesn't form a carbocation intermediate. So the table illustrates that E2 is indeed possible for primary, secondary, or tertiary alpha carbons. Now let's focus on this cell of the table. Notice that when we're in this cell of the table predicts that usually the mechanism will be SN2. But we've seen there's an exception. With tert-butyl oxide and a primary alpha carbon, you'll get E2. Well, now I'd like you to pause and explain that exception. Pause the video and explain why tert-butyl oxide will favor E2 over SN2. Well, you should know that this is what tert-butyl oxide looks like. And the key fact about tert-butyl oxide is that it is a bulky base. It has a lot of bulk, it has a lot of methyl groups waving around, creating a lot of steric hindrance. Tert-butyl oxide creates a lot of steric hindrance. It kind of gets in its own way, so to speak. Tert-butyl oxide gets in its own way. All these methyl groups waving around could block the O- from attacking another molecule. Now, if tert-butyl oxide has so much steric hindrance, why does that favor E2 over SN2? Well, we know that the big obstacle to an SN2 reaction is steric hindrance. Since the big obstacle to an SN2 reaction is steric hindrance, well, since tert-butyl oxide has a lot of steric hindrance, it's unlikely to be good at an SN2 reaction. Tert-butyl oxide will be poor at carrying out an SN2 reaction because of all the steric hindrance. The methyl groups will get in the way and block the O- from joining the alpha carbon. Now, why doesn't that also hinder E2? Well, remember, tert-butyl oxide does have a lot of steric hindrance, but steric hindrance that blocks the base is not a big obstacle to E2. Steric hindrance is not a big obstacle to E2, so even though the tert-butyl oxide has a lot of steric hindrance, that does not hinder E2 very much, and therefore when we have this bulky tert-butyl oxide base, we're more likely to get E2 rather than SN2. That explains this exception. Remember that the deeper reason here is if we used this tert-butyl oxide as a nucleophile, it would have to actually join the other molecule. And the methyl groups get in the way and prevent the O- from getting close enough to join the other molecule. But if we use the O- as a base, it doesn't have to get close enough to the other molecule to join it. It only has to get close enough to take a hydrogen from the other molecule. So tert-butyl oxide doesn't have to get that close to the other molecule to act as a base, and therefore the steric hindrance is not going to slow down the action of tert-butyl oxide as a base as much as it would interfere with the action of tert-butyl oxide as a nucleophile. So we've used the material that we discussed to get a deeper insight into this table and to understand why tert-butyl oxide favors E2 over SN2. One more, somewhat more subtle point. We've said here that steric hindrance is not a big obstacle to E2. Notice the wording, it's not a big obstacle. I worded it that way because I don't want you to think that steric hindrance could never be a factor in E2. steric hindrance can slow down E2. It just doesn't slow it down as much as SN2. And here's a case where that's relevant. We've discussed that usually the major product for E2 uses the more substituted beta carbon. But we've seen that tert-butyl oxide is an exception. Tert-butyl oxide prefers to attack the less substituted beta carbon. Why does tert-butyl oxide prefer to attack the less substituted beta carbon? Because it has less steric hindrance. Tert-butyl oxide is a bulky base that creates a lot of steric hindrance, so it's easier for it to attack a beta carbon that has less steric hindrance. So notice that this is a case where steric hindrance is a factor in E2. This is a case where steric hindrance is a factor in E2. So notice that we would say steric hindrance is not a big obstacle to E2. Steric hindrance is not as big a factor in E2 as it is for SN2, but you shouldn't think that steric hindrance can never play a role in E2. The Hofmann rule for tert-butyl oxide is an example where steric hindrance does play a role in determining the outcome, even for E2. Well, the material we have on the screen now is an important summary of a lot of key ideas for E2, SN2, and SN1. A lot of these are ideas that are likely to come up on your exams. So now would be a good time to pause the video and make sure you have all of this information memorized. I know that's kind of complicated. There's a lot of information here, but this is all stuff that definitely could be tested on exams. So you should have all of this information memorized. And also, you should be able to justify all of these ideas. We gave a justification for all of these ideas. Most of these are ideas that we justified in terms of the rate determining step. So make sure that you have all these ideas memorized and make sure that you can justify all of these ideas. In many cases, you should be able to justify them using the concept of rate determining step. Notice that it's important when you learn this material to use complete sentences. For example, you can't just say that it requires a good nucleophile or that nucleophile quality matters, because SN2 requires a good nucleophile, but SN1 doesn't. So always give a complete sentence that includes what mechanism you're talking about. Don't just say that nucleophile quality matters, say nucleophile quality matters for SN2. Don't just say that it requires a strong base, say that E2 requires a strong base. When you learn each fact, include the name of the mechanism in the fact, because there's different facts for different mechanisms. When you take your exam, the professor is probably going to try to switch gears back and forth between a variety of different mechanisms to confuse you and trip you up. So to avoid that, you have to learn each fact with a clear label for which mechanism the fact refers to. Don't just say methyl alpha carbons are best, say methyl alpha carbons are best for SN2. Don't just say tertiary alpha carbons are best, say tertiary alpha carbons are best for SN1. Don't just say it is possible for primary, secondary, or tertiary alpha carbons, say E2 is possible for primary, secondary, or tertiary alpha carbons. When you're learning these facts, always label which mechanism, which type of mechanism the fact refers to. So here we have a summary of factors that favor or disfavor E2 reactions, as well as SN2 and SN1. But remember that in the previous video, we learned that when E2 occurs on a cyclohexane ring, there are special considerations that can favor or disfavor the E2 reaction. Do you remember what are those special considerations that affect the rate of E2 on a cyclohexane ring? Well, here's the answer. For a cyclohexane ring, we learned in the previous video that E2 can occur only while the ring is in the chair flip that puts the leaving group in the axial position. While the ring is in the chair flip that puts the leaving group in the equatorial position, E2 cannot occur. Therefore, E2 will proceed quickly for a ring for which the more stable chair flip puts the leaving group in the axial position. And if you have a ring for which the less stable chair flip puts the leaving group in the axial position, E2 would proceed slowly for that ring. How do you figure out which is the more stable chair flip? the more stable chair flip would be the one that puts the largest substituent in the equatorial position, and the less stable chair flip would be the one that puts the largest substituent in the axial position. These ideas are a little complicated, but we illustrated them in the previous video. So my point is, if you see a problem that asks you to compare two E2 reactions and decide which E2 reaction will proceed more quickly, well, here are some of the important factors that can determine whether an E2 reaction will proceed more quickly or more slowly. But also, if the problem is asking about an E2 reaction on a cyclohexane ring, it could be that the key to answering, if the problem is asking whether an E2 reaction will occur more or less quickly on two different cyclohexane rings, then the problem might be testing these ideas. In the next video in this series, we will look at example problems that illustrate how these ideas might be tested on exams. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.